You'll notice in this chapter the transport layer and the network layer have been put together. Layer 4 on the internet model is the transport layer, and layer 3 on the internet model is the network layer. The network layer is responsible for linking the application and network layers together, and that's because it's in between them. It's also responsible for segmentation and reassembly, meaning each packet comes in a small segment that gets broken down so it can be transported. And once it's broken down, the receiving end needs to be able to reassemble the segments and put them back together so the data is useful. So that's what they mean by segmentation and reassembly. Now, in the internet model, the transport layer is considered session management. However, if you look at the OSI model, session management, or the session layer, is its own layer, and I want you to understand that. Transport layer is also responsible for the end-to-end delivery of messages, meaning that is the layer that says the message will arrive or will not arrive. The network layer is responsible for the addressing and routing of the messages. In other words, it works with the switching, and it works with the IP addresses to route messages and switch them and get them from point A to point B. Thank you. The TCP/IP protocol actually exists at two different layers. The TCP protocol exists in the transport layer, and the IP protocol exists in the network layer. So together, you commonly hear the term TCP/IP, and that's how that term gets derived. It was originally developed as a single internet working protocol by Vint Cerf and Bob Kahn in 1974. Later divided into TCP and IP protocols. It's the most common protocols of the internet in LANs, WANs, and backbone networks. So everything you do on the internet today is pretty much TCP/IP. You wouldn't have the World Wide Web without TCP/IP. Keep that in mind. Thank you.
All right, let me talk about the TCP protocol, which is the Transmission Control Protocol. It's the most common transport layer protocol. A PDU is called a segment, so the protocol data unit is called the segment. It's used for reliable transmission of data. So as we'll see pretty soon, TCP is session controlled data transmission. In other words, a session is established with TCP. With UDP, it is not. So each header is about 160 to 192 bytes with 20 to 24 bytes of overhead. Optional fields are not required. So here we can see the different information that's sent with the TCP protocol data unit, and we can actually capture that being sent. So we have the source port, or the port on the source machine that sent the message, the destination port where it's going, the sequence number, so what transmission number it is so it can be reassembled. It has an acknowledgement number. It has the H length. It has a bunch of different flags that we can take a look at. These are acknowledgement and SYN flags, which are used in communication. You'll have checksums, urgent pointers, padding, and finally you'll have some of the data. So by now you should all have Wireshark installed on your machines. I did put it on this laptop here, and I'm going to go ahead and capture some information, and we're going to see some of this information here from a real trace. And this one, it'll look different for everybody because everybody's got their own networks here. So you should be able to see something similar though. So right now I'm going to fire up Wireshark, and I am on a Wi-Fi connection right there on my Mac. So I'm going to choose that right there. And then I'm going to click on the shark to begin capturing packets. So right now, we can see a bunch of packets being captured. Actually, there's not that many packets here. I'm going to wait for something else to happen. I don't want to show you a UDP packet, but here's one, and it shows that it's an acknowledgement. So that being said, I'll stop here. So obviously, I have some kind of web page open or something that's making this communication here to this destination. I'd like to see what that is, but we will show you that in a minute. So let's take a look here. This is a TCP packet. Now you'll notice right here we have, when I click that, you can look in the center, and you have these different arrows and these different points right here. Now this is interesting. We know that the transport layer is the 4th layer on the internet model, and there are 4 different points here. So we know that there's 5 total layers. However, some of these layers exist at the application level. So let's take a look here at, while we're doing this, because this will start to bring some of the class together so we can understand the concepts of encapsulation, which is where all the PDUs get put together and transferred along. This is the information that's in them. So if I open this right here, I'll be able to see that this is an Ethernet connection. If I dig down a little bit deeper, I can see that I'll be able to see that it's captured on interface 0. I get some time delta information in here. If I want to look at the layer below this, that would be the data link layer. I can open that up. I can tell that this is the destination's adapter. This is the MAC address for it, which we'll get into in a second. I can see that the source on this one is the Apple, which is the computer I'm using right now. I can tell that it's an IPv4 connection. I can open some of this up. I can get some very interesting information out of this. And I want you to remember that this address is an Apple address, and I want you to see the way it's listed here, right there, and look at that. Maybe even take a screen print if you're looking online, because we'll come back to that. Then we know it's an IP, using the IP protocol, and that's going to have its information. But now let's look at the TCP protocol, where right away we can see the source port, the destination port. We can see the source port, the destination port. We come back here again. We can find our sequence number. We can find the stream index. I mentioned some of these flags right here, which all coincide. These flags all coincide right here with these right here. And so on and so on. I get the window size. There's the urgent pointer. I get the checksum values, the sequence acknowledgement analysis. So I get to, whoops, I did not mean to do that. I can see all of that right there. There's the urgent pointer. There's options. So all of this information is contained and can easily be derived from Wireshark, which is why it's a very powerful tool. There's also a much more low-level way to do this within Linux, and we might get into that depending on how the class is going. But I wanted to point that out right now because that should tie a lot of this together that we're seeing, and now you should be able to actually see a PDU get transferred, and it should make a lot more sense. And if you'd like, you can even stage up some of your own transports and stuff. If you have a web page that you want to go to, you can trace that web page. So I'm going to get back to this trace in a minute, but right now we need to continue our slides. So on the next slide, let's talk about the user datagram protocol. So here it goes.
The UDP, or the user datagram protocol, does not establish a session the same way a TCP protocol will. You need to look at it like you're throwing a baseball with a message, or you're throwing a ball with a message. So the sender would be the person throwing the ball. The receiver would be the person catching the ball. So with the UDP protocol, you're going to throw the ball to the specific person, and you're going to expect that that person's going to catch it. And if they do, they will receive the message. And if they don't, then they will not receive the message. So a lot of times it's really a nice protocol to use if you need to send something out there, but you don't want the whole system to halt and wait for the message to come back. It's simply a nice way to establish a quick connection. As you can see, there's nowhere near as much overhead in the size of the packets being sent. So it does have a useful point. Most DNS requests, for example, are UDP. And we'll go into DNS a little bit later as well. But it's also important to remember that UDP has a PDU, and that PDU is referred to as a segment. It's used in time-sensitive situation for control messages or when reliability is handled by the application layer. So a lot of times, like I said, it just throws the message out there, and it's not concerned about the reliability of the message. It just hopes it gets the message back. So that's what they mean when they say the reliability is handled by the application layer. Thank you very much. Now we're going to talk about the IP protocol, or the Internet protocol. There's two different versions, and they're both very different. There's IPv4, which is probably what most of you are used to seeing. It's the most common version of IP. There's 32-bit addresses, so you might have seen addresses, and I'm making this up, like 25.173.124.6 or something to that effect. That's an IPv4 address, and there's only so many possible combinations. So IPv4 is running the risk of running out of address space, and that's a big concern. So nowadays, people are beginning to adopt the IPv6 standard, but it's much more difficult, and people are much slower to adopt. The IPv4 exhaustion hasn't hit a critical point yet, so people are still trying to get away with using IPv4, including myself, because it's a very difficult standard, and we've all been using IPv4 for a long time. So the fact that not many people are comfortable with IPv6 does create a security situation and a security risk, because people don't know how it works and don't know how to use it. So IPv4 is pretty much the standard that we're all still using, but IPv6 is available, and it has been around for quite a few years now. Thank you. Now we'll discuss linking to the application layer. So the TCP and the UDP protocols may serve multiple application layer protocols. So what does that mean? TCP is always going to be the underlying layer, as we've shown in our Wireshark trace and in other traces as well. So what that means is the TCP and the UDP protocols work with IP addresses and port information to transport information. Just looking at the list below, we can see that HTTP, HTTPS, FTP, SMTP, IMAP, POP3, DNS, what have you, they all reference TCP ports or UDP ports. So that's what they mean when they say it serves multiple application layer protocols. And these are just some common port standards. There's thousands and thousands of ports available. In fact, there's 65,535 total ports available. And many, many private companies have written a lot of proprietary protocols and a lot of proprietary products that use these various ports that we've never even heard of. A lot of times configurations will use random ports, and again, they'll use proprietary protocols. I've created tons and tons of web servers that haven't used the standard 443 and port 80 standards. So there's many ports and many combinations and many, many, many different application protocols that all rely on the lower layers, especially the transport layer, which uses TCP and UDP. Thank you.
Please take a minute and review this diagram. Please notice the ports that are used at the application layer on both the client machine and the server machine, and try and get an idea of how linking application layer services to the transport layer are set up and done. Thank you.
Now let's talk about segmenting. As we said, UDP and TCP packets are referred to as segments. So segmenting involves breaking up large files into smaller segments and putting them back together. Remember, that was the segmenting and the reassembly that we discussed. Segments may be passed individually to the application layer or after reassembly. So again, there's some flexibility with how that's set up. So how large are segments? Again, I've talked about the negotiation and the handshake. So how large are segments? Size depends on the network and the data link layer protocols. MSS is the maximum segment size. And again, that's negotiated or agreed upon during the TCP handshake. So for example, if the maximum size of the data in an Ethernet frame is 1500 and TCP and IP use 20 byte headers, the maximum segment size is 1460 bytes. So again, the maximum segment size is negotiated during the TCP handshake, and that's when the network speed and the type of physical medium is determined. Thank you. I know we discussed UDP as being connectionless in a previous slide, and I gave an example. TCP is, on the other hand, connection-oriented, where a session is actually created, and that is the distinction. So think of a session as a virtual circuit between two communicating devices. You could think of a walkie-talkie conversation as connectionless, and you could think of a telephone conversation as a conversation where a session has been created. So TCP connections are opened using a three-way handshake. There's the SYN, the SYNAC, and the ACK. And sessions obviously are more reliable. So if you want to have a reliable communication where the communication is critical, you'd probably use TCP. It also contains a lot more overhead. Thanks. So, addressing exists at all layers. It's used to direct messages from source to destination. Addresses are assigned in various ways. System administrators can assign an address. ICANN can establish an address, and we're going to go into that and what it stands for in later chapters. It's very important. And there's been a lot of recent history with ICANN. And hardware can deal with addressing, as we'll see, and that includes vendors and what have you, and we'll see that as well. Addresses exist at different layers. I've already said that. Addresses can be translated or resolved from one layer to the other. So, for example, ARP does address resolution at the switching layer or the data link layer. DNS uses translation at the network layer, and we'll see that as well. So please look at the graph below. It'll give you an idea of addresses and where they lay and what they do. Thank you. Network layer addressing most commonly is displayed in 32-bit representation of IPv4 addresses. You look at below, you see the binary notation. Those are called octal sets. There's 4 octal sets. As you can see, 129.79.78 is all represented, .193 is all represented below. I did discuss binary in previous slides. It is important that you know binary and know how these numbers are derived. I drew the Excel graph. You could create one of those yourself and figure out the decimal notation. This is very useful when it comes to writing net masks, which I have a link on a future slide in this chapter that will go into that and do a very, very good job. And it's critical that you know this. For the on-ground students, it'd be interesting if you are on campus and at a DOS prompt, you type in ipconfig and hit enter. And look at Albertus's net mask. It's very interesting. It's different than you see at a lot of other places. So keep that in mind. Like I said, there'll be a link on a future slide that's very, very good at explaining this. And I will hold you to some of it. Thank you very much.
Now let's talk about addressing. A portion of an IP address represents the network, and the rest of it represents the host. We'll explain this a little bit more later. There's classful addressing. It uses the first bits to determine the number of hosts. It's kind of discontinued now, but the nomenclature is still used. Now it's classless interdomain routing, or CIDR. It uses subnet masks to more flexibly divide address space into subnets. So let's look at this IP address below, the 129.79.78.193. Now, because of its subnet, the 255.255.255.0, we know that this is a Class C network in which the first three positions are represented in full. The 255 will block those out because that means that is completely reserved space. Therefore, those numbers are dedicated. So 254 characters are included in the last field, which is the 193, because the 0 is offered. 2 bits are always taken by the number 0 and the number 255. So those numbers can never be used. I have a slide on the next slide. I'll have a hyperlink, and I'd like you to read that and understand it. It might be a quiz question because it's very important to understand that, and I don't believe the book did a good enough job of explaining it. So please follow the hyperlink and try and understand those concepts. Like I said, I'll probably have a quiz question on it. Thank you.
Okay, so for the last 2 slides, I've hyped up this hyperlink here. So learn it, live it, and love it. Thank you. So now we're going to talk about the concept of dynamic addressing. It is possible to set up a static IP address for a machine. However, for most user computers, this can become very time-consuming and monotonous. If you're in a large IT staff at a large company like, let's say, General Motors, and you need to roll out and deploy a bunch of PCs for workers on an entire floor, you don't want to spend the time to sit and configure each computer with its own network settings and to give it its own IP address. You'd rather have a central device known as a DHCP server to do that for you. So it makes life a lot easier, and it's not always critical for the end user to have their own dedicated IP address. However, most of the time, they will continue to have the same IP address. I worked at a job that had a 7-day lease on the IP addresses, and that was known as the DHCP lease. It's very common to have a lease with an IP address. I was never gone for more than 5 days straight in 3 years, so I never got a new IP address. Whereas a friend of mine, she always went on vacation, and her IP address changed all the time because her lease would expire. So that's very common for DHCP addresses to keep your address for a substantial length of time due to leases. If you want your computer to get new IP addresses assigned, you could shorten a lease period. But DHCP is the most common protocol for dynamic addressing. Your device will send out a broadcast message saying, hey, I need an IP, and the DHCP server will respond with your settings. And you see that almost all the time on your local networks with your routers. You see it actually with your cable installs as well. Those leases are dynamic. You don't have a designated IP from your ISP. They give you a DHCP lease as well. So DHCP is very common when it's not important to have a dedicated IP address for a server. Thank you.
Now let's talk about address resolution. So first we need to understand that the MAC address is the physical address, not of your computer, but of the network adapter that your computer is using. MAC addresses are resolved and translated into IP addresses through the use of the Address Resolution Protocol, or ARP. There's an example of a PC ARP request to the left. Host or server name resolution is where an IP address is actually translated into a host name. We can see this with the University of Indiana, for example. www.indiana.edu translates to 129.79.78.193. Domain name service is what does the resolution. There's a really good slide on the next slide. The next slide is really good. It has a diagram of DNS and how it goes and resolves in the order that it looks. That's important to know. One other thing to realize is if DNS cannot resolve an address, it may also check in your local host table on your computer. In this example, I'm going to manipulate the host table just to show you how it works and how host tables can also be used to translate server names. So without further ado, here we go. I'm also going to get back to this. I'm going to click on this link right here as part of the example. So bear with me, because you'll like this. This is really interesting here too. And I did touch on this earlier when I was showing you the Wireshark trace. So that being said, let's get back to our current Wireshark trace here. Right here, where we have the actual MAC address right here in parentheses. And this says Eris Grow here. And down here on the source it says Apple. And it's got a MAC address here. So I know I'm using an Apple, and I'm pretty sure that my Apple's using an Apple network card. So the first 3 digits of a MAC address, remember these digits here are hexadecimal digits, identify the vendor of your network adapter. Because remember, we're at a lower layer here. And that's what it uses to translate with the switch. So that being said, what I'm going to do this time is I'm going to go in here under View in Wireshark, and I'm going to go to Name Resolution, and see, you can tell it was already set to resolve the physical address or the MAC address. So now I'm going to also check this. Oh, look at that. It already resolved my address right there. And then I'm going to come here and I'm going to resolve the transport address as well. Oh, and there it goes right there. It shows you how it just translated it with these requests here. So now if I create a new request, and I don't need to save this, and right now it's doing a filter. I don't need that filter either. So now I can see some traffic coming through here. It looks like it's communicating using DNS here with my with some of my routers here, and you can see that there's a lot more information being shared. So let's stop it right there and let's take a look at this DNS request. All right, let me shrink some of this down here. So you'll notice that DNS is an application layer protocol, and it uses At the transport layer, it's using UDP. And at the network layer, it's the IP protocol, IPv4 specifically. And it's using Ethernet 2 with the source and destination again here. So that is my router, obviously. And at the frame level, it's showing things at the physical level as well. So you can see all the different groups are represented here. I'm getting the ARP translation out of this. I'm doing all the address translation available, and it makes things much more readable. I now know what some of these devices are. So I look at something like this. You know, I can look here at the different layers. It's 4 here. At this level, it's more than that. If I want to see this TLS layer, that's a protocol layer. That's the SSL layer. That's a application layer protocol. So it's sending something there at the application layer. It's using HTTPS most likely, or it's using SSL. So actually it's using SSL. So we have some very good, interesting information there. And I can sometimes follow the stream here. I could follow the SSL stream. And there's not a whole lot there to read, unfortunately. But that's a good example of how Wireshark works and what it will do. And here's the next slide that I was talking about going from. Thank you. Actually, before I do that, there are a couple other things I want to touch on here. I was going to talk about host table resolution here. So what I can do is I can ping e-learning. We can do this with just about anything. .albertus.edu, and this will keep going until I exit. So I can see that I have an IP address right there for albertus.edu. Okay, so now if normally I would just edit my host file, but there's some things I have in there that I don't necessarily want to share. So I'm gonna, whoops, not that one. So I'm going to put the IP address in there. We'll call it CIS325.com. And now, when I go ahead and write that, oh, whoops, that's right, I'm not editing it. So let me redirect that to the host file. Sorry about that. I'm used to doing these as edits. So I'll add that to the bottom of my Etsy hosts file. Then when I come into here and I do CIS325.com, it'll automatically translate my address and redirect me to e-learning. So I did that by modifying my host table. This is the example of how a DNS request works. So it's important to follow these steps here, step 1, step 2, step 3, because your resolving name server is going to check at its local root server. So it's going to check at your organization itself to see what their DNS has on it. And if it doesn't find the name that it can resolve, it's going to try again at the top level domain server or the TLD server. This would exist through probably your ISP or something at that level. If it can't resolve it there, it's going to try and authenticate it through an authoritative name server. And hopefully that works. So this is a really good diagram of the network layer functioning and how a DNS request goes through the different steps. So it starts with you can think of it as starting with the server closest to you and working its way up the chain till it can resolve the name. And now I will play this from the current slide.
Now let's talk about routing. Routing is the process of identifying what path to have a packet take through a network from sender to receiver. It involves routing tables. Routing tables are used to make decisions. Routing tables show which paths to send packets on a given destination. Routing tables are kept by computers making routing decisions. Routing is done by routers. Routers, as hardware, are special purpose devices used to handle routing decisions on the internet, and they maintain their own routing tables. We will see that there are such things as level 3 switches or layer 3 switches, also called VLAN switches, that make a lot of routing decisions, but they are thus not routers. Thanks. Let's take a look at all the different paths possible to get from point A to point G. I've listed some below. Thank you.
Now let's talk about traceroute. So traceroute will count the number of hops that a server will take to get from its source to its destination. In this example here, I'm doing a traceroute to WTNH.com. And as you can see from my connection, I can make it in 13 hops. On a Windows machine, it's trace RT. On a Mac, it's going to be trace route. So I will try trace routing WTNH again one more time. So here we go. So trace route on a Mac. And TNH.com. And I'd be curious to see if it follows the same path. Here it's trying to move forward, but it's not, it's timing out here. So it knows where it wants to go. Oh, there it goes. And it's made 9 hops already. And it's really trying to get there. It's at 14 hops right now. It's not uncommon for one of these traceroute requests to time out after 30 hops. And I also noticed that from this previous traceroute that WTNH used to be a WordPress website, and it was not anymore. So it looks like it's within the network right now. If I were to look right there, I can see that 54.209.238 is probably related to one of these subnets right here. This 54 is probably a Class A network, and they're probably blocking my traceroute request. But I can't verify that. It certainly does look like it though. So I'd guess that 54 is a Class A network like we saw from Computer Hope on that URL I listed previously. And I'm guessing this is going to time out. So that's no good. Let's try something different here. Let's try traceroute www.albertus.edu. Or actually, I've done Albertus already. Let's do yale.edu. So trying to get out of my switch right now. There it goes. So we can see that the 32.223.104 is obviously a Frontier gateway. And there it goes. So it took 10 hops to get from my living room to Yale.edu, and that is a complete round trip, start to finish request. So that's how trace route works. There's also visual trace routes. If you wanted to go onto the internet, we could open a new tab. We could do something here like visualtraceroute.com. Let's do that, visual trace route, and see what we can come up with here, okay? I think that could be interesting. Oh, why didn't that work? Let's try it here. This was one I remember here, so let's try that. And let's put in Yale.edu here, and this one's nice because it shows the entire world, which I like. So isn't this interesting here? So it's showing that from here it took 13 hops, because you got to remember now it's doing this, it's probably doing this trace route starting from the location at Montes, not at my house here. Although it does look like it's close. It looks like it did start around here. But you can see it, that Yale.edu could be actually hosted in California. So that's quite possible. Let's take a look. Down here we usually get some better ideas as to what's going on. So here's some of the hops. It shows the connection speed and information. So this does look very similar to the trace route that I had originally done. It does look like it jumps through to California though, which isn't probably the most efficient way to make the connection. So let's try and compare it and see what we get with our trace route. So you can see here initially that these are totally different. It's using a west location. This actually looks like it could be an Amazon Web Services IP address possibly. It's somewhere generic in the west, so it does follow a different route up until, actually it follows an entirely different route. So that's important to know, that this trace route comes from this website right here and not from my local computer. So going on, let's go to the next slide on routing, and we'll discuss the concepts of centralized versus decentralized routing.
Continuing with routing, we'll discuss centralized routing and decentralized routing. With centralized routing, there is one router or one computer that makes all the routing decisions. This is not very common anymore, as networks change dynamically everywhere, whether they're small networks or large. Decentralized routing is where the decisions are made by each node independent of one another. So at each hop, the routing decision is made there. We saw the hops with the trace route in the previous slide. Information needs to be exchanged to prepare routing tables. So in order to prepare the routing tables, there's a lot of information being updated and transferred. That's what they're saying. And this is used by the internet. Quite frequently, very, very few internet providers do not use centralized routing. It creates more reliability as multiple routes are possible, as we've also seen in previous slides. Thanks. Again, with routing, we are going to discuss static and dynamic routes. Static routes are fixed routing tables. They're manually configured by network managers, and they're locally adjusted by these managers when different machinery is added or removed. Dynamic routing involves routing tables being periodically updated. Routers exchange information using various protocols to update the tables and to optimize them. So static routing involves fixed routing tables. Dynamic routing, the routing tables get updated periodically. Thank you. Now we'll discuss dynamic routing algorithms. continuing our discussion with routers and routing. The distance vector algorithm is based on the number of hops between two devices. Again, we remember seeing hops from our trace route example above. Link state algorithms base their calculations on the number of hops, circuit speed, and traffic congestions. Therefore, since more criteria is involved, it provides more reliable, up-to-date paths to its destinations. But those are the two primary dynamic routing algorithms. Thank you. Now we'll go into some routing protocols. The RIP protocol, or the Routing Information Protocol, uses a dynamic distance vector algorithm, as we discussed, and it's used for interior routing. It's useful in small, less complex networks. So the RIP, or the Routing Information Protocol, is useful in smaller, less complex networks, and it is based on the dynamic distance vector protocol. Thank you. Another common routing protocol is the OSPF, or the Open Shortest Path First protocol. It's a dynamic link state protocol used for interior routing. It's the most widely used interior routing protocol on large enterprise networks. So your big companies where you have large floors and rooms, this is a very common routing protocol. And it's very, very reliable. Thank you. Now let's go into some multicasting concepts to round off this chapter. There's the unicast, which is one computer to another, so you have a single line of communication across the network. A broadcast is where one computer broadcasts to all computers in the network. I've seen that in a lot of classroom situations, not at Albertus, but at other schools. Broadcast professor messages are very common. A multicast message involves one computer connecting to a group of computers, like a video conference. And this is useful when the same data needs to reach multiple receivers and avoid transmitting for each receiver. So it's particularly useful if access link has bandwidth limitations. It's got many implementations at different layers. And in IP multicasts, the host dynamically joins and leaves multicast groups using the IGMP, or the Internet Group Management Protocol. So multicasting is very, very highly established at this point. At one time or another, you've probably all worked with each type of multicasting like this. Thank you.